We will start with the next topic, that is ideal solution. You have heard ideal gas in the previous year in the topic states of matter. A gas which obey Boyle's law and Charles' law at all temperature and pressure, or it obey the equation P is equal to nRT. And here in this chapter we have to study ideal solution. Then what is ideal solution? The solution which obey Raoult's law. Solution which obey Raoult's law. Which law? Raoult's law number 1. I have given you two laws, Raoult's law 1 and Raoult's law 2, Raoult's law 1. Both solution and both solvent and solute are volatile. Second one, delta V mixing equal to 0. Delta V mixing equal to 0. And third one, delta H mixing equal to 0. Delta H mixing equal to 0. If these three conditions are obeyed, automatically that solution is said to be ideal solution. Ideal solution. We will see what is delta V mixing. Delta V mixing equal to 0. What is delta V mixing equal to 0? The volume change during the formation of solution should be 0. You are taking solvent, we will take solvent as A, 100 ml A plus 50 ml B. You will get 150 ml of AB. 150 ml of AB. So here, the amount of solute and solvent 150 and the product is also 150. So delta V is equal to 150 minus 100 plus 50. So volume change is 0. Volume change is 0. There should not be increase or decrease of volume. And third one, delta H mixing equal to 0. Delta H mixing equal to 0. What is the meaning of delta H? Enthalpy change during the formation of solution should be 0. No heat absorbed or liberated. No heat absorbed or liberated. No heat absorbed or liberated. If these two conditions are obeyed, then automatically it will obey Raoult's law. Then we can say the solution is said to be ideal. So a solution is said to be ideal when it obeys Raoult's law, delta V mixing equal to 0, delta H mixing equal to 0. We can say another way of stating ideal solution. A solution is ideal when AB attraction is same as AA or A or BB attraction. A or BB attraction. AB attraction means solute solvent. Solvent solute attraction should be same as solvent solvent or solute solute attraction. Then delta V mixing will be 0, delta H mixing will be 0, then it will obey Raoult's law, then it becomes ideal solution. We will see some examples of ideal solution. Examples of ideal solution. The examples of ideal solution are benzene and toluene. Benzene and toluene. Second one, toluene and xylene. Toluene and xylene. Then normal hexane and normal heptane. Normal hexane, normal heptane. Then you have a chlorobenzene. 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 The formula is C6H5Cl and bromobenzene. And bromobenzene. Bromobenzene has a formula C6H5Br. Then you have ethyl chloride C2H5Cl and C2H5Br. So this is first example, second one, third one, fourth one and fifth one. So these are the 5 examples for ideal solution and they are very very close to ideal behavior, and in these cases you can take benzene as A, toluene as B, or you can take toluene as A and benzene as B. So you can, these are the 5 examples of ideal solution. We will look into the graphical representation of ideal. Graphical representation of ideal behavior, ideal solution. This is a graphical representation. So you have to draw the graph. Here in the x-axis you have to give concentration, and the concentration term normally given is mole fraction. Mole fraction. Mole fraction, you know, here chi A is equal to 1 and chi B is equal to 0. And here chi B is equal to 1 and chi A is equal to 0. Here in the y-axis you are putting vapor pressure. Vapor pressure. And here also the second y-axis you are putting vapor pressure. Vapor pressure. So here only you have A is present. So we can write the vapor pressure of A as P0A. P0A. And here the vapor pressure is P0B. And you can see the height of P0A is greater than P0B. That indicates A is more volatile than B. You can draw like this. The height of P0B is small and P0A is small and P0B is high. That indicates B is more volatile than A. So now I am going to prepare the solution. You are taking A in a vessel and you are adding B into it. And you are studying the vapor pressure of A. you can have this a curve or a line like this. This is a line, and this line indicates decrease in vapor pressure of A. Decrease in vapor pressure of A by addition of decrease in vapor pressure of A by addition of B. By addition of B. And another line from here. And this line indicates decrease in vapor pressure of, this is a line from here to here, and this is from P0B to this point. And this is a decrease in vapor pressure of B by addition of A. By addition of A. And here you have another line. That is all possible ideal solution of A and B. All possible ideal solution of A and B. All possible ideal solution of A and B. All possible ideal solution obtained by mixing A and B. And we can write P is equal to PA plus PD. P is equal to PA plus PD. Or you can write P is equal to P0A into Chi A plus P0B into Chi B. So this is this line indicate all possible ideal solutions of A and B. So this is the graphical representation for ideal, and here you have Chi A1 and here Chi B1. So when Chi A is 1, no Chi B. Chi B is 0, or mole fraction of B is 0. So we can put P0A here and P0B here. So this line represents all possible ideal solutions of A and B. I will give you one more statement. Let P0A is equal to 250 mm of mercury. Imagine 250 mm. And P0B is equal to 150 mm. And all possible solutions of A and B should have the vapor pressure in between the 250 and the 150. It should be in between 250 and 150. It should not be greater than 250 or it should not be lesser than 150. The value should be in between 250 and 150. All possible ideal solutions have vapor pressure in between 250 and 150 mm of mercury. The ideal solution, because we have taken P0A as 250 and P0B as 150. So all possible ideal solutions have vapor pressure in between 250 and 150. Non-ideal, we have to study non-ideal solution. A solution is non-ideal when it is not obey Rolle's law. Not obey Rolle's law. Not obey Rolle's law. And second one, delta V mixing not equal to 0. Delta V mixing not equal to 0. And third one, delta H mixing not equal to 0. So these are the three conditions for non-ideal solution. A solution not obey Rolle's law, delta V mixing not equal to 0, and delta H mixing not equal to 0. We can classify non-ideal into two types. Number one, positive deviation from Rolle's law. 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 Second one, negative deviation from Rolle's law. Negative deviation from Rolle's law. So non-ideal solutions are again classified into two types. Number one is positive deviation from Rolle's law, and second one is negative deviation from Rolle's law. Well, this is the first one. There is a positive deviation from Rolle's law. Positive deviation from Rolle's law. So what is positive deviation? First one is positive deviation from Rolle's law. The solution will show positive deviation. Delta V mixing is positive. Delta V mixing is positive, and delta H mixing is also positive. Is positive. These two are positive. So we will explain what is delta V mixing positive. You are taking 100 ml of A plus 50 ml of B. You are getting 151 ml of AB. So there is an increase of delta V is an increase of 1 ml. Normally it is in between 150.1 and 150.9 or 151 ml, but sometimes it may be 150.5 ml. So anyway, for simplicity I am writing 100 ml of A plus 50 ml of B. You are getting 151 ml of AB. So delta V is positive. And why the volume increases? Because AB attraction is AB attraction or AB interaction is less than AA or BB attraction. A or BB attraction. AB attraction is less than AA or BB attraction. That means there is some slight repulsive effect between A and B. So when repulsion happens, when there is repulsion between A and B, there will be an absorption of energy. In order to repel from A, B absorb energy. To repel from B, A absorb energy. So energy is absorbed. So we can say delta V positive and delta H is also positive. Delta H positive, endothermic. So after mixing the solution, if you touch the vessel, if you touch the bottle, if you touch the beaker, it will be cool because it absorbs energy. So delta H is positive, delta V is positive, and delta H is positive. Such solutions are positive deviation. I will give some example. The examples are ethanol and water. Then you have methanol and water. Methanol and water. And the next one is propanol and water. Then our next one is cyclohexane and benzene. Then acetone and CCl4. Then you have acetone and carbon disulfide. So these are examples of solution which show positive deviation. Study at least 3 examples. For positive deviation. We look into the graphical representation of positive deviation. So what will be the graphical representation of positive deviation? We'll see the graphical representation is, this is the graphical representation. Here we have concentration, here we have vapor pressure, here also vapor pressure, and the concentration is normally mole fraction, chi A. So chi A equals 1 and chi B equals 0, and here you have chi B equals 1 and chi A equals 0, and here you have P0A, here you have P0B. So the dotted line represents the ideal solution. This is for ideal solution, and here now we are having the positive deviation. The vapor pressure is greater. So the vapor pressure is greater than that of pure A and B. So this is all possible solutions of A and B. All possible solutions of A and B. All possible solutions of A and B. All possible positive deviation. Solution which show positive deviation from A and B. So this graph, this curve, the curve which is above that of Rod's law. This dotted line represents that of Rod's law and our ideal solution, and this is a curve that show positive deviation from ideal behavior. So positive, for positive deviation, delta V is positive and delta H is positive. Delta V is positive and delta H is positive. Next, second one is negative deviation. Negative deviation from Rod's law. In this case, delta V is negative and delta H is negative. These two are negative values. We will see 100 ml of A. You have taken 100 ml of A plus 50 ml of B. The resultant volume of solution will be 149 ml of AB. So 149. So there is a decrease of 1 ml. Delta V is minus 1 ml. Volume decreases. Why volume decreases? There is some attraction between, due to attraction between A and B. Due to attraction between A and B. So whenever an attraction forms between A and B, attraction means a bond. It may be a chemical bond, it may be a weak force, it may be a strong force. Whatever the bond forms, when attraction forms between A and B, a bond forms between A and B. Then energy will be liberated. Or released. Delta H is negative value. So delta V is negative and delta H is negative. So such solution, after preparing such solution, you just touch the bottle, you touch the beaker, you can feel the hotness. So you can feel the solution is found to be very hot because delta H is negative, the process is exothermic. So we have a lot of examples. You take H2SO4 and water. Second one, HNO3 and water. Then third one is HCl and water. HCl and water. Then the fourth one is acetone and pyridine. Acetone and pyridine. Then chloroform and ethanol, or chloroform and acetone. Chloroform and acetone. Chloroform and acetone, or another example, chloroform and ethanol. So these are examples of solution which show negative deviation from Raoult's law. Negative deviation from Raoult's law. H2SO4 and water, HNO3 and water, HCl and water, acetone and pyridine, chloroform and acetone, and these are examples of solution which show negative deviation from Raoult's law. We will see the graphical representation of negative deviation. So the graphical representation is this. You know, this is a solution which show ideal behavior. So here the curve comes below that of ideal. So this is a solution which show negative deviation. So this is all possible solution of A and B. All possible solution of A and B. Of A and B. So here you have concentration, here you have vapor pressure, here also you have vapor pressure. So this is a negative deviation. So you have three graphs. First one is ideal solution, second one is a positive deviation, and the third one is a negative deviation. So we look into the next topic, that is azeotropic mixer. Azeotropic mixer. So what is meant by azeotropic mixer? What is azeotropic mixer? So the term azeotrop means constant boiling mixer. Azeotropic mixer. Azeotropic mixer. Azeotrop means constant boiling mixer. Constant boiling mixer. Actually, this is not in your syllabus, but you should be familiar with this term azeotrop. So what is azeotropic mixer? Means constant boiling mixer. We will consider the first one type. Solution which show positive deviation. Solution which show positive deviation. Positive deviation. A and B combine to give a mixer C. A and B combine to give a mixer C. And you know that for positive deviation, the total vapor pressure of the solution will be greater than that of A and B. So C has high vapor pressure. C has high vapor pressure than A and B. C has high vapor pressure than A and B. And so C has low boiling point. C has low boiling point. So the mixer C will boil it. Mixer C boil it a low temperature. At a low temperature than A and B. Then A and B. Composition of C. Composition of C. Composition of C in vapor phase and liquid phase. Vapor phase and liquid phase are same. Liquid phase are same. Same. So this is called. So C is called azeotropic mixer. C is called azeotropic mixer. Azeotropic mixer. It has low boiling point, so it is low boiling azeotrope. It is low boiling azeotrope. It is low boiling azeotrope. So I will explain once again. Imagine the situation: you are mixing A and B, you are getting a mixer C. C has high vapor pressure than A and B, so C is having low boiling point. The mixer C boil at a lower temperature than A and B. The composition of C in the vapor phase and in the liquid phase are same. If you examine the composition or concentration of C in the vapor phase and in the liquid phase are same, so we can say C is an azeotropic mixer. So I will give you an example with a graph. This is a graphical representation for azeotropic mixer. See, here I am putting concentration. Here I am putting percentage, and here I am putting temperature. Temperature. Instead of putting vapor pressure, I am putting temperature. Here you have 100% A, 100% A. Here 100% B. You know, in the previous graph for positive deviation, P0A is having maximum height, so the boiling point will be very low. So here I am putting TA. So what is TA? TA is the boiling point of A. And here I am putting TB. What is TB? TB is the boiling point of B. Boiling point of B. And A and B combined to give a mixer C. Mixer C is having low boiling point, so I am going to put it here, C. So the curve comes like this. This is a curve. Here it is vapor, here it is liquid. Here it is vapor, here it is liquid. So at this point you have both the vapor of C. C is having vapor phase composition and liquid phase. These are same at this point. And here it is a boiling point of C. So Tc is a boiling point of C. So I can write here. Tc is less than Ta and Td. Composition or concentration of C in liquid and vapor phase are same. Liquid and vapor phase are same. So C is called azeotropic mixer. C is called azeotropic mixer. So C is this. So I will give you the example that A is water. So A is ethyl alcohol. We take A as ethyl alcohol. You know the boiling point of ethyl alcohol is 351.3 Kelvin. And B is water. You know the boiling point of water is 373 Kelvin. C is a mixer. Ethanol and water. And the percentage of ethanol is 95.5% and water is 4.5%. And the boiling point is 351 Kelvin. You can see 351 less than 373 and 351.3. So the boiling point of C, and this C is called a rectified spirit. C is an azeotropic mixer.